Hi, in this video, we will discuss the application of integrals in the determination of hydrostatic pressure and force. Before we continue, there are some important facts that you must know. First of all, you can see in the figure, in a particular depth, the pressure of the fluid, such as water in the tank, apply the force equally in all the directions. And this pressure is known as hydrostatic pressure, which is the pressure present within the liquid when it is at rest. So at D equal to 0, which is the water level, the pressure is 0. As we increase the depth, the pressure will be increased as well. And this pressure can be calculated by rho GD. Rho G is a constant approximate to 9810. So this figure shows the hydrostatic pressure acting on horizontal wall as well as vertical wall. So try to find out the direction for the pressure. You should observe that the direction of the pressure is always 90 degrees to any surface in contact with the fluid. For the horizontal wall, you can see that the pressure is equal because the depth is the same. While for the vertical wall, the depth keeps increasing, so in this case the pressure is increased as well. Let's start with the horizontal plate case. In this case, you can see that same amount of pressure is acting on the plate because the depth is the same. And the force can be equal to pressure multiplied with area, where the pressure is equal to rho GD. The derivation is given as well, where you can see force equal to mg. M is the mass of the fluid above it, and M can be equal to rho V, and V can be further reduced to D depth multiplied with the area. By using this formula, we can solve the following example. In this case, we have a swimming pool where the bottom of the swimming pool located at the 2-meter depth. Area of the bottom wall is 5 meters squared. So by using this formula, first we can compute the pressure to be equal 19.6 kilopascal, and we can find the hydrostatic force at 98 kilonewton as well. Once we get the force, normally engineer will conduct stress analysis to check if the bottom wall structure is safely used or not. Next, we are going to find the hydrostatic force acting on the vertical plate. In this case, you can see there's a dam with the dimension of 50 meter width and 20 meter depth. The water level is 4 meters from the top of the dam. And you can see that the front view, 3D view, and also the side view. Let's look at the 3D view. So the 3D view shows you the right triangular pressure distribution. We show you that if the depth increases, the pressure will increase as well. In other words, it means that the amount of pressure and force acting on the plate is different at different depths. In this case, we cannot apply directly the previous formula that assumes the depth is constant. Let's assume that the depth is x while the width is y. It can be seen that the previous formula can be used to find the hydrostatic force Fi equal to Pi Ai, which is here, let's say. And the area of this force is equal to Wi delta x. So we can use the same method to find the force at any depth. And if we take all the summation of the force, we can find the resultant hydrostatic force. Finally, the formula can be rewritten into the analytical format. So in this case, you can see that the resultant force is equal to integration from A to B with respect to x direction, and rho Gx indicates the pressure while W dx indicates the delta A. So by using this formula, let's continue to find the hydrostatic force. The global axis is rotated for the ease of visualization here, and the limit A and B are obtained at 0 and 16 here. When we integrate the function y equal to 25 with respect to x-axis, we are actually able to find the hydrostatic force acting at one side only. So we have to multiply 2 to get the resultant force at two sides. So by substitute the rho g 9810, the 2 multiplied 25 you get 50, which is the total width function. And solving this easily by basic integration rule for polynomial, we can get this answer. Let's practice more example by using the hydrostatic force integration formula here. In this example, the trapezoidal dam has the width of 50 meter at the top and 30 meter at the bottom. The depth is 20 meter. The water level is 4 meter from the top of the dam. We rotate the global axis for the ease of visualization. As you can see, the width changes in a linear pattern, and therefore we can use the general formula y equal to mx plus c to find the width function, which is in red. So by using these 2 points, we can find the slope to be negative 0.5 and the intersection to be 23. By integrate this width function with respect to the x-axis, we can find the force at one side and multiply it with 2, we can get the force at two sides. By substitute the rho g and w inside this formula, we get this integration function. And by integrate the x, we get x squared over 2. By integrate the x squared here, we get x power of 3 over 3. By substitute the lower and upper limit inside this formula, you should be able to get this answer. Let's summarize the important remark in determining the hydrostatic force. Step 1 is to decide the global axis, where we always put the x-axis towards the depth of the water. Where you can see the x-axis is moving from the water level to the depth, and it split the item into two symmetric parts. Next, the y-axis must be in water level, like this. In step 2, we have to find the width function y, and it depends on the geometry. For example, the width function is increased in a linear pattern here, where we can use y equal to mx plus c. So once you solve the m and c, which is the slope and intercept, you get the y function. For the second case, the circle, the equation for the circle is like this, where once you get the center AB and the radius r, you can substitute and get the y function. You have to be careful in this case because for this quadrant, this width function is always positive. Therefore, we have to remove the negative part. Step 3. Integration formula. So this is the formula to determine the hydrostatic force, which is equal to 2 multiply the integration for the pressure multiplied with dA. Pressure is rho gx and dA is y dx, where you can easily find the y dx by substitute the previous width function. And you can get the hydrostatic force at one side without the 2, and multiply with 2, you get the hydrostatic force at both sides. Using the same method, it can be applied to any geometry. In step 4, which is the final step, we have to apply the integration method. So for case 1, we have this hydrostatic force, where we can see the integral involves the polynomial function x squared and x, which can be easily integrated by using the basic integration rule. So we get this answer. Substitute the upper limit 3 inside and minus with the 1 substitute with lower limit 0, we get the final answer. For the case 2, we are going to find the hydrostatic force acting on the semicircle as shown in the figure. So this function looks more complicated than the previous one. To simplify it, we use the substitution. Let u equal to x plus 2, du equal to dx, and we are able to simplify into this. We expand it by multiplying u to the square root function here and multiply negative 2 to the square root function here. And we are able to separate it into two integrals. So for the left integral, we can further reduce it by using the substitution. Because you differentiate the u square, you get the 2u, which is relevant to this function. So let's use the substitution t equal to mx squared minus u squared in this case. For the right integral, we found that this is in the form of a squared plus b squared, where we can use the trigonometric substitution where we let u equal to x sine angle in this case. Continue with the left integral. We obtain this function which is in polynomial. So we apply the basic integration rule for polynomial function. We get this result. Substitute the lower and upper limit inside and we get the final answer. For the right integral, after we substitute the substitution, we get this answer. Let's try to extract the x squared constant to outside. We obtain this, and 1 minus x sine squared is equal to cos squared by using the identity. And with that, we can further simplify it into cos square function only. So cos square function can be further reduced to cos by using this identity. So in final product, we can see the cos function and the constant 1 over 2. With that, we use the basic integration function for constant and the cos to find the final product. Apply the lower and upper limit inside this function, we get the final answer. Finally, the resultant hydrostatic force can be computed, and the answer is 1688337 Newton. So far, if you can master the skill mentioned in the important remark section, then you should be able to solve the hydrostatic force problem easily. This appendix serves as extra information for your better understanding. So we would like to discuss global axis here. The recommended global axis is shown in the left figure here, where you can see the area dA can be computed from y with function multiplied with the dx. And the v function can be found from the geometry here. In this global axis, your depth is the same with the x-axis. Therefore, the pressure is equal to rho dx. And substitute the pressure and dA into this formula, we are able to compute the hydrostatic force. On the other hand, we can use another global axis as shown in the right figure. The area is slightly different, where you can see the dA is equal to v function x multiplied with dy, where the x function can be found by using the same approach. In this global axis, your depth is not the same with the y-axis, where you can see at d equal to 0, which is at the water level, your y will be 6. And at d equal to 6 here, your y is equal to 0. From this relationship, we can find that d is equal to 6 minus y. So we substitute the pressure and area inside the formula, we obtain another integral. We can use another global axis where we locate it at the center of the circle and we obtain another integral again. By solving these three integrals, we found that the hydrostatic force is the same. This means you can choose any global axis to find the same answer. So the recommended global axis, of course, is the first approach because it's the easiest one. The other global axes are shown because there are many references are using it. So you should use it as extra information. So far, we can use the integration method to find the hydrostatic force acting on the horizontal surface here as well as vertical surface. The hydrostatic force acting on inclined surface and curved surface require more advanced fluid mechanics knowledge. Therefore, it is not covered in this study. In summary, hydrostatic force identification is very important to ensure safe structural design and avoid failure in many engineering structures such as dam and swimming pool, as shown in the figure. In order to achieve this, you should master good integration technique to solve the problem.